Now I think we are ready to start today's webcast with an exciting talk. My name is Morten, and I'm the host for today. I'm an R&D engineer here at Anybody Technology. And today you're going to hear from our two presenters, which is Kimmo from University Hospital in Turku. But the work that we're going to talk about today was something Kimmo did as a postdoc at Aalborg University, working together with Professor Michael Skipper Andersen. And Michael Skipper Andersen is actually here with me today at the office, recording this webinar, and Kimmo is with us on a mobile data connection from Finland. So it's going to be exciting. The outline for today is that I'm just going to give a brief introduction to the Anybody modeling system, and then you're going to hear the actual webcast, and in the end we'll have a questions and answers session where you can ask some of the questions and we'll discuss the content. Just a short introduction to the Anybody modeling system. It's a musculoskeletal simulation tool where you can take motion data, kinematics and forces as input, and it can allow you to compute or simulate body loads that could be joint moments, muscle forces and joint reaction forces. The Anybody modeling system is used in a wide variety of applications, from product design and optimization, ergonomic analysis, surgical planning and outcome evaluation, load cases for final element analysis, and finally movement analysis. And what you're going to hear about today actually encompasses many of these areas here, from movement analysis to final element analysis, and also some outcome evaluation. A typical workflow with the Anybody modeling system could look something like this. You would maybe come with your own motions and forces. That could be stuff that you measured in a mocap lab, for example. Then you would combine it with body models that you may have designed or built yourself, or reused models that others have created. And you maybe also come with your own environment that the model works in. In this case, it's an example with an exoskeleton. Then you run simulations on your model to calculate the internal body loads, muscle forces and joint forces. And those you can then output, analyze them directly or output them and use them for post-processing, for example, in final element tools. And some even close the loop completely and do design optimization, where they then change their environment or device that they are simulating. But with that short introduction in mind, I'm going to give the word to Michael, who is sitting right here with me.
Thank you, Morten.
I will also just make you the presenter, Michael.
So, thank you, Morten. I think you should be able to see my screen now.
Yeah, that's good.
Just move the mic a little bit closer. Yeah, so this work that I would like to present to you today is something that was done under an EU project called NEMO, which was about the biomechanics of knee osteoarthritis. And it addressed everything from epidemiology all the way to biomechanical interventions. And I'll show some of the work here today together with Kimmo, what we did on estimating the loads in the cartilage. So just a very brief introduction to knee osteoarthritis, or osteoarthritis in general. So it's a slow degeneration of cartilage, bone, meniscus, and ligaments, and it causes pain. And actually the knee is the most frequent site of osteoarthritis, and is listed among the top 5 causes of disability worldwide by the WHO. So there are lots of interventions, and the typical ones are actually just pain management. But there are some biomechanical and non-surgical interventions, and those we would like to talk about. So all the surgical interventions we will not be addressing here. So some of them would be like a lateral wedge, which has the intention of shifting the load or shifting the ground reaction force more lateral. There are weight training or strength training has also been shown as positive for pain and cartilage following knee osteoarthritis. There are different types of braces as well. So braces like here in the middle, these are so-called soft braces, so they don't have a much of a mechanical effect, but they probably affect proprioception. At least that's the hypothesis of how these work. Then there are the common valgus braces, like we see here, which tries to apply a valgus moment to counter the knee adduction moment. I will talk about that on the next slide. And then there are gait modifications to try and teach people to walk in a slightly different way to alter the loads in the knee. And wedges and knee and gait modifications are the topics for today. So just an introduction. So the most common way that these interventions are addressed or evaluated in the literature is to look at the knee adduction moment, which is that if you take the ground reaction force here we have under the foot, and then you take the moment arm that goes from the knee center out to this ground reaction force vector, then this creates a knee adduction moment. However, it has been shown in multiple studies that it might not be a good surrogate of the internal loads in the knee. I've just put 2 references here, but there are many more out there to show that. So what we would like instead is to see if we can come closer to the biomechanics occurring in the knee. So that was the aim of this work, which was to develop a patient-specific workflow to estimate both whole body loads and also loads at the tissue level. And that's exactly what we'll be doing today. And it's split into the part that I will talk about the whole body part, and Kimmo will talk about the tissue loads. And the typical way you would do this would be to use musculoskeletal models on one side. So we use those to estimate the overall or gross loads of the body. And then we'll use much more detailed the finite element simulations of the joint to figure out what happens in the cartilage, and even what the fluid pressures are and the fibril strains are in the cartilage. But Kimmo will get to that. And the purpose here was to do it on a subject-specific basis, not simple, normal, generically scaled models. So the study design we did, so we started by doing it on one subject, which is the pilot data, and this is what we'll show the whole workflow on this one subject, and then we'll show some preliminary stuff we have done on actual patients. But that arises a whole new set of questions, and even some questions we will ask to the audience today on how to go about this. So we started with MRI scans, because those we think we can do on patients if we can argue that in the end it will have an effect. And we did it in 2 scans. We had a full lower limb scan with coronal slices. So we had in a fat suppressed scan, so you can segment out the bones. And then we also did the Osteoarthritis Initiative detailed knee scan of both knees of this patient. And then from that, we spent a lot of time segmentation, which is the bottleneck right now. So automatic segmentations of MRI images would help a lot in generating fast models in this case. So we segmented out the full bones for the full lower limb scan, and then we segmented all the tissues out of the detailed scans. So both the ligaments and cartilage and meniscus and and everything from that. Then from the full lower limb scan, we generated a patient-specific model. We did that by using some of the morphing techniques that are available in Anybody and in Mimics. There are multiple webcasts on how to do morphing out there. So if you want to really dive into how to do this, I would recommend that you find one of the old webcasts. We also use the scans to identify the hip joint centers, the knee axis, and the ankle axis for having subject-specific joints. And so that was the patient-specific model part of it. Then in the lab with the subject, we got subject-specific lateral wedges generated from imprints and then 3D printed. So these ones were state-of-the-art insoles that people will use for lateral wedges. And then we equipped the subject with a whole set of lower extremity markers and asked the subject to walk in different ways that we wanted to investigate what is the effect of this on the tissue load. So we had normal walking trials. Then we had a 5-degree lateral insole. We had a 10-degree lateral insole. We had toe in and we had toe out with a wide stance. And we even had some medialized knees and other activities. But these are the ones I will show results for. Then we combined those 2 things, and then we did marker tracking. So we took our scaled musculoskeletal model, and then we got that to track the markers from the lab so that we have kinematics out of that. And then we want to use that for inverse dynamic simulations, where we take the measured ground reaction forces, apply them under the foot, and the movement from the kinematic analysis, and then use that to estimate the muscles and the joint reaction forces. But in this process, we actually have multiple ways that we can try to represent the knee joint. So we could do, the typical thing would be that we do a hinge knee, which is a simple door hinge, which has its limitations in some ways. We could also select one of our more advanced joints, which is based on this force-dependent kinematics. There are also multiple webcasts on that. I'll show it on the next slide what we did. And then we have also very recently developed a new knee joint model, which we call the moving axis model. Now I'll show that one as well. So this is just choices of how to try and represent the joint from an overall mechanical point of view without going to full finite element analysis at this point. Yeah, so the one we ended up using is this model that you can actually see here. So it's the two bones, well actually the three bones, so femur, patella, and tibia are assumed rigid, and then we equipped it with nonlinear elastic contacts between the contacting surfaces, so between the cartilage that we segmented from the bones, and then we also used nonlinear elastic elements, nonlinear elastic ligament models, so that we only drive the flexion angle from the data from the markers, and then we predict all the detailed movements of the joint using this model. And there's one relatively recent paper out about how we do these ones. It's called the Introduction to Force-Dependent Kinematics. And it's also described in this paper in scientific reports where the whole workflow is published. Another idea which has just been published in Journal of Biomechanics is what we call a moving axis knee instead. So the drawback of doing force-dependent kinematics or finite element analysis is that it can be relatively slow. So what we have developed instead is to make a model that only uses two poses measured on the subject. So we use a 0-degree information and a 90-degree piece of information of the bones. In this case, it was obtained from EOS X-rays, so two poses of the bones of the subject. And then we use that to generate a knee model, actually the one you see up here on the top, by estimating where the joint center is at full extension and where it is at 90 degrees, and then assuming that it moves linear from one to the other. We could, of course, also take a hinge. So Kimmo will show some of the results when we put a hinge in this model and also when we put a force-dependent kinematic knee model in here. So we don't have this moving axis knee model out, but I hope we will in the future. Yeah, so once we have done that in there, depending on how we choose the knee model, we're going to get some results out. So which would be, for instance, here, that could be the knee adduction moment, or it could be the medial contact force, or whatever else you can get out of musculoskeletal simulation. So we could end here with the musculoskeletal model results, or we could continue on to the finite element models and then use these results as the boundary conditions in this case. So if we just for now stick to the results that we would be getting if we took this one subject here. So this is the gait cycle. So from 0 to 100% gait cycle, and we have the knee compressive force here in Newton, and we have the different modifications that we looked at. So if we just start by the black one here, which would be the normal gait. So that is even debatable whether or not you want to reduce or increase the load in these patients here, but I think that's a discussion beyond this webcast. But assume that we want to reduce the load on the medial contact force right now, then it looks like doing toe in for this particular subject would be the ideal modification that we did. Doing medialized knees for this particular subject would seem like the opposite result. So we took this one step further. So we started to do it on patients. So in the first, we thought we could just go ahead and do that, and it would just be straightforward as you would be doing it on the healthy. It turns out it's not the case, and especially when we get to the finite element stuff, and Kimmo will discuss that. So we did get MRIs of 5 patients, but we have 6, but we have only completed 5 so far. We spent a lot of time doing segmentation of all of these ones, which was also actually harder to do in the patients than it was in the healthy subject, just because the bones are more deformed and more osteophytes, and there are other issues coming up when you want to do it on patients. But we did generate the same patient-specific models in each case, so you can see the subjects are actually quite different, so quite small, quite tall. And then for each of those, we also had them in the Gait lab to walk in different ways. So here just illustrated for one of them. So for each of the subjects, we have the normal gait here with shoes, and we have the toeing in, toeing out, and we have the wide stance. So that we did then for these five patients. And I'll just show what the musculoskeletal results then turns out to be. So these are the medial contact forces for these 5 different patients. So we have the one with shoes. Normal gait would be in the black here. And then our different modifications. We even included a 0-degree insole, but that should give relatively small changes relative to a shoe. But it was just to have the possibility of isolating the 5-degree insole from a 0-degree insole from a shoe. But one of the things that you can actually see is that the loading is actually, response here is actually quite different from the different patients. So if we just take and compare for now patient 1 and 4, and take a look at the toe in activity, which would be here. So that would look like for patient 1 that's having a significant reduction on the first peak. It does also reduce the second peak, but not as much. But if you apply that same modification to patient 4, you're actually going to get mid-stance, much higher loads. And if you take a look at patient 4, there again, toeing in seems to be a good idea. If you take a look at patient 3, then toeing in has almost no effect. It has a tiny effect over here, whereas toeing out has a positive effect on this. So it's not a very clear response. So that if you give toe in, that will work. And I think this could be potentially explanation of why there's a lot of conflicting evidence on whether or not these interventions actually work, because if it's in one patient reduces the load and another patient increases the load, then on average you're probably going to get nothing. So I think we need to identify who needs what, and I think the models can be used for that, at least on an overall loading level at this point in time. And I would just like to remind you that we had this one patient where we did it all on. So just because this is what Kimmo will continue on. So this is our normal healthy subject where it looked like toeing in was a good idea. And with that, I would like to hand over to Kimmo for his finite element discussion on this.
Thank you. Thank you very much, Michael. I will see if I can get Kimmo online.
I can hear you just fine. How about you? Can you hear me?
Yeah, it's okay, and we also see your screen.
Oh, wonderful.
So Kimmo, before you get started, I just want to remind all the attendees that if you want to ask questions, then now is a really good time. Now you just heard Professor Andersen talk. Open the questions and answers pane and type in your questions there, and then we'll try to address them at the end. But Kimmo,
okay, so thank you. So I'm Kimmo Halonen. I worked as a postdoc for Miguel and others in the AAU Cartilage Turku University Hospital. So the question is, since we have the compressive forces from the musculoskeletal stuff, why do we even need finite element modeling? Well, the problem with the loads is that they don't tell you the whole story. First of all, the CAM moment, the knee adduction moment, which is the typical indicator used in plenty of publications, that's been shown to be inaccurate. It doesn't predict the actual loads that the cartilage goes through. And even though you get actual compressive forces from the musculoskeletal stuff, that doesn't take into account the geometry of the knee. So, for example, if you have a huge load but it's distributed differently over a wider area, then you also get lower stresses, and that doesn't really tell you what the cartilage is going through. So that's why we need finite element modeling. So just a brief introduction if you're not familiar with this technique. So finite element modeling, the idea is that we cannot solve analytically all the equations in a tissue at every single atom. So what we do is we divide the tissue into small blocks or discrete or finite elements, and you can use, for example, hexahedrons or tetrahedrons, or you can use squares in 2 dimensions if you want, and there are plenty of other element types. And once you divide the structure into these finite elements, then what you need to do is you assign boundary conditions and also material properties, and those material properties should be tested versus real data. So basically you need to test test the tissues in a laboratory and define parameters from there. That's what we have done. Not the testing, but using the verified parameters. And the way that this is enforced is that we take detailed MRIs of the subject's knee joint, and we segment the different tissues. This is a really lengthy process, followed by an almost equally lengthy process called meshing, where we divide the whole thing into these finite elements and assign the boundary conditions and so on and so on. And how does this relate back to Mikael's musculoskeletal stuff? Well, the musculoskeletal output is used as an input in the finite element model, so it drives the model. And we actually use a fairly detailed and sophisticated material model for all the soft tissues. The model is called fibril reinforced poroviscoelastic model, which is a biphasic model that takes into account many of the cartilage's features, including the depth-wise collagen fibril architecture, proteoglycan distribution, the water content, and you can do all of that stuff even depth-wise, so you can vary it as a function of the depth. And the ligaments and tendons were defined as linear springs, and the bones were defined as rigids, because we know from previous research that's accurate enough. And one thing that we also have that plenty of other models don't have is we have the split line patterns. So if you're not familiar with the split line pattern, if you take a needle, dip it into an India ink, then poke a hole at the cartilage, after a while the hole stretches into a line, and if you do that in plenty of places, you get these split line patterns. So they are kind of like the preferred direction of the fibrils in the surface, so we also take that into account. So just to remind you, you are probably familiar with the structure, the morphology of articular cartilage. Just to remind you that we are talking about healthy articular cartilage at this point, so we are testing this with one healthy subject. And what it means is this type of structure. We will later on tackle the early OA and severe OA structures, but at this point we are using this kind of structure. So now we have the MS input, which we use to drive the knee. And what we get as an output is this distribution of forces, I mean stresses and strains on the cartilage surface, but also in the deep tissues. Although for this study we only studied the surface stresses and strains, because, well, there was a lot of data, and this time we only focused on the surface. So initially, the results indicated that the insoles seemed promising, especially the insole 10 degree. And also we had other interesting initial results. However, this was done with the simple hinge knee joint model. And there were some issues there. The biggest issue was that we had high tibial contact pressures. But we didn't really know initially where this resulted in, because all of the loads were realistic, and we had the sophisticated musculoskeletal model, which was kind of derived from the one that won the Grand Challenge competition. Even our deformations were realistic. So what was going on? And so we set out to investigate where the issue might lie, and we took several actions to find out what was wrong. And first of all, we did some parametric studies with different muscle models. Secondly, we figured that because the subject that we had was a healthy young woman, and most of the data, especially the implant data, comes from elderly OA patients who usually have a weakened extensor strength. We figured that maybe those forces that are reported from those implant studies, they might not reflect the ones that are observed in a healthy subject who obviously doesn't need an implant to measure. So I figured that it might be worth to test whether varying the extensor strength in the model would influence the contact pressures. We also decided to change the simple hinge joint into a more complex force-dependent kinematics from now on FTK model. And what we found out was that this was the change that we did to the muscle model. So initially we had simple muscles, just one element, and what happened when we changed those muscle models into a 3-element muscle model, we saw a huge drop in the contact pressures during the first peak of the stance phase of Gait cycle. So this was clearly one of the key contributors to why the stresses, the contact stresses, were so high. So when we did this change, we saw that the contact pressures in the medial tibial cartilage, they dropped across all of the studied walking styles, so normal, insoles, and the Gait alterations. And what we also did was we studied the extensor strength, and please bear in mind that this extensor strength is done with the hinge model, because it's a lot more difficult to sort of vary the extensor strength when you have this complex knee joint where that moves around and is constricted only by the ligaments, because there it's a lot trickier to vary the strength of the muscles. But with the hinge joint, it's relatively simple. And what we also saw here was that the peak was significantly decreased when we dropped the extensor strength. So these two were clearly contributing to the high stresses in the cartilage surface. So what we decided based on this is, first of all, to change the muscle model into a 3-element model one. But secondly, we also decided to go with the more complex FTK model that is only constricted by the ligaments, so also more realistic. And just here, I want to highlight that the FTK model with the healthy subject with full strength is somewhere around this area. So we already expected higher axial reaction forces there. So just to remind you that this is the complex knee model that we ended up using. Looks pretty good. So what we saw there, so these are the peak deformations during the stance phase for femoral cartilage, lateral and medial tibial cartilages. And if we compare these to those reported in the literature in an MRI in vivo study during Gait, we see that they are right in the middle of the range that is reported. So this material model and also the forces seem to be really nice. And now we have some actual results. So these are the surface. This is the axial view of the tibial cartilage. On the left, you have the lateral medial side, and on the right, you have the lateral side. So first of all, we are let me just show you which one. So we are first discussing the first peak here, and the second peak force is here. Okay, so during the first axial peak force, the normal gait showed this kind of peak contact pressures, and what we saw that neither of the insoles were able to reduce the peak pressures in the tibial cartilage surface in either one of the compartments. And the toe in was able to reduce the peak pressures by a little bit, surprisingly on both sides, and so was the toe out wide method. During the second axial peak force, what we saw again was that the insole 5 degree was unable to reduce, even elevating the peak pressures in the tibial cartilage. The insole 10 degree was able to reduce them on the medial side, but it doesn't really help if the peak forces are increased during the first peak force, because the overall you haven't really helped the patient. In the toe-in method, unfortunately, we observed an increase during the the second axial peak force in the medial tibial compartment, and the same thing also happened with the toe out wide method. So none of these methods seems to be very good, but there are some things that puzzle me, which I will tell you more about in the next slide. Because so what's going on there? How is it possible that some of the peak pressures have been increased? I want to go back here to tell a little bit about these pressures here. So one of the reasons why these peak pressures are elevated is because the contact area has changed just a tiny bit. And for example, if you have a reduction in the contact area, and you have the same force, that means that your peak forces are going to increase. So that's one of the issues. But there's also something else going on, and I want to show you this. So these are the average contact pressures, fibular strains, fluid pressures, and other variables during the stance phase, and we are looking at the medial side only at this point. So if we take a look at, for example, the insole 5 degree one, we can see that the medial tibial reaction force is increased. So that means that the subject is somehow walking differently using these insoles, and that's also one of the contributors to why the peak pressures are elevated. And you can only make assumptions as to why that is, but the subject, she seems to be walking a little bit differently by wearing these insoles. You can also see that the insole 10 degree has the same issue. This also, the second peak also, you can see that the normal gait, which is the red dashed line, now the reaction forces are pretty much the same as with the insole 10. And if you remember from the previous slide, that was the point where the insoles were actually able to reduce the peak forces. So it might be possible, but it's really hard to tell. And also, if your subject is going to walk differently and use more force using those insoles, then there's not really any point using them. Okay, so further on, if you look at the other values, they were fairly similar all around in all of these. I want to highlight here the maximal principal stresses. That the only area where the other gauge alterations were able to reduce the stresses were during the second peak, and the ones that were able to do that were the toe out wide method and also the insole 10-degree method, as shown previously. So do the insoles work? Well, if we look at the lateral side, it's not that they don't redistribute the load in a different way than before, because if we look at this one is slightly off, but it's supposed to show at the first peak here. So if you look at the average loads, stresses and strains on the lateral side, we can clearly see that there's a huge increase there with at least during the first peak force of the stance phase. So the insoles seem to be deloading the medial side, but they don't seem to work, not at least with this subject. I want to remind you that this is only one subject. This might be subject specific completely. So to conclude, we have developed this very subject specific analysis, and we believe that this method may be able to evaluate the stresses and strains that the knee goes through during the normal gait, and also other activities if used on patients in the future. And as a core reminder, I want to remind you that both of the insoles were unfortunately unable to reduce peak pressures and stresses and strains apart from the second peak. And the same goes for the other alterations. And just to remind you once again that this is only one healthy subject, we need to repeat this with multiple subjects, and preferably with multiple OA patients, which, by the way, is what we have done, but it's a work in progress. That's the next thing that I will show you now. So those were the ones that we have actually published in this article, and this next bit, what I'm going to show you, is the work in progress part. Okay, so with patients, we are talking about this kind of articular cartilage structure. So if you're not familiar, I presume that most of you are. In the early osteoarthritis, what you get is you have this degeneration of the organized collagen fibril structure. You also have an increase in water content in the surface, and in the late stages of the osteoarthritis, the whole cartilage starts to wear down. You lose more and more of the collagen architecture structure, and you increase the water concentration and so on. You also get these changes in the subchondral bone, etc., etc., etc. It's a complex disease. So these are the ones that we are modeling at this point. So the way that we model the early OA structure is that we first of all we change the superficial orientation of the fibrils from parallel to the surface into random structure, like in the middle zone. And what we can also do is change the water content, the prostaglandin content, and so on. But I won't go into details. And in the severe OA, just like I showed you before, we changed the geometry of the structure according to the MR images. So where you have lesions, we take those into account, and we also apply these degenerated collagen fibril structures there. I'll tell a little bit about that in the very last slide, but for now you have to believe me. So this is how it looks like with the OA patients. So highlighted here with the red circles, we have the defects that these patients have here. So you can see that they all have medial OA, although not all of them in the tibia, with patient number 5 had femoral medial OA, and it goes without saying, but modeling this is significantly tougher than healthy subjects. And there are also some extra steps that you need to go through if you attempt to do this. For example, what we did that was different with the healthy subject was that we also modeled the subchondral bone. So instead of defining the bones as rigid structures, you also need to segment the bones, and you need to mesh and assign material parameters to the subchondral bone, and also take it into account when you define boundary conditions. And we did all of that. And lastly, I want to return to the collagen structure, because some of the challenges are that when you have this worn out cartilage, you also definitely have changed cartilage parameters. But how do you actually assign the correct parameters to the cartilage? Well, I think the best way to go about this is to prepare beforehand and actually image the cartilage using MRI and with the correct sequences, where you can see some of the inner workings of the cartilage, especially the collagen fibril structure. There's a really nice article from Razan and al. Discussing this. You can also model some other parts like the project, like in structure, but that is not as significant as the cartilage. The collagen distribution. So what you need to do is you probably need to image those, and you need to apply them into these tissues, and that already is a whole new, really difficult step. So if you're willing to do that, go ahead. And lastly, I want to acknowledge my co-workers Kristin Jalo, Marko Manisi, Mikko Venäläinen, Mark Desi, and of course Mikael Skipper Andersen. Thank you.
Thank you very much, Kimmo, for the nice work. So I'll just make me the presenter again. So Michael, one of the first questions that came in is thanks for your interesting webcast. Could you elaborate on the validation of your models, and to what extent your variation in your results is due to parameter uncertainty or actual interesting subject specificity?
That's a very good question, and something we have been thinking a lot about. So before we even started to apply any of this on these, and even on the healthy subject, we went through the trouble of making exactly the same subject specific model on some of the total knee replacement patients, because there we have measured load, and that we have also published, and there we got relatively good results. So in terms of scaling and morphing and all of this, that's the same approach. And then the next thing we did was, then you bring in of course, a healthy knee, but then you don't know the forces anymore. And as Kimmo showed, there we had taken a look at what is the deformation that you see in the cartilage, and that people have measured in the literature. We haven't done that yet on a subject-specific basis. We have some work ongoing, but we have done biplanar X-rays to measure the kinematics of the knee, and then compare that to the deformations that we see predicted. But of course, it's a very good question. How accurate this is in models like this, and I think at some point we're going to have to do like a leap of faith on the situations where we can't stick in an instrument, because we're looking for parameters that you can't measure. I think what we could do is, of course, do some of these sensitivity studies that Kimmo also showed. And what we found there was, for instance, on the muscle model, was that, yeah, sure, it changes the peak stresses, but the relative change between one intervention, that seemed to be the same, independent of model. So, you know, if you wanted to conclude whether one model is better than the other. But a lot of parameters and a lot to do still on this topic.
Yeah, it's an interesting area. So next question here: which boundary conditions do you extract from your musculoskeletal models? Maybe Michael, you can answer this one.
True. So what we did was that on the femur, we defined one point, and then around that point, we summed up all the contributions from the muscles, the hip joint reaction force, and gravity and inertia. So the things we didn't include in that force was the reaction force between patella and femur, and the ligaments, and between femur and tibia. Because those we wanted to model in the finite element model. So everything that wanted to include in the finite element model was not included in this sum. And then we did the same on the patella. So we summed up all the muscle forces, inertia, and gravitational forces on patella, and then those we applied. And then we kept tibia fixed in the finite element model.
Makes sense. I think the next question here might be a question for you, Kimmo. For the tibial femoral contact pressures during the actual peak forces results, did you confirm your results with multiple trials for each?
I assume that can you hear me, by the way?
Yeah.
Okay, good. So I assume that the person asking the question means that.
I can't hear you.
Hello.
I hear you fine. It's okay. Kimmo.
Okay.
It's just Michael's earphones that stopped working. So.
I assume that the question is that whether we simulated multiple trials from the same subject. So say that the subject walked, let's say, 20 times, and we would record 20 times and model it 20 times. Unfortunately,
I believe that's what they mean.
Unfortunately, that is not feasible. What we did do is that I think there were 5 trials for each type of gait alteration, as well as the normal walk. And what we did was we kind of took the one middle of the pack one trial out of each one of those. We tried to prioritize that. First of all, we tried to make sure that it wouldn't be an outlier, so it did in the middle of the pack. And next, we also wanted the length of the stance phase to be as similar as possible to the healthy one, because if your stance phase is significantly longer than the normal one, then you're bound to have a lower impact in the knee, and then you have artificially lower stresses. So we wanted to make sure that wouldn't happen. And the reason why it's not feasible to actually model multiple trials with the FE model is because it's extremely difficult to get the models to work. They take a lot of time to even run through. It's basically one day each, and a lot of computing power. So that's why usually in these studies you only see a few models. I hope that answers your question.
I think it did. Thanks, Kimmo. And another question here is, have you guys also investigated deeper flexion type activities, and specifically impact of loads experienced in the patellofemoral joint? Maybe Michael, you can elaborate on that a bit.
No, that's actually a very good idea. So the ones we did so far were the ones that are these typical interventions, the gait modifications that people are using, and then insoles, because they're also receiving a bit of attention. But I think it's a very good idea to do, and I think the workflow to do it, at least up to the musculoskeletal loads, even on the patients, that is, that we can do, and that's set up so we can do it in a not too difficult way at this point in time. We still need to resolve all the finite element issues to get to the full results on the patients there. But I think it's a very good idea to do. So if you want to go down that route, I encourage you to do so.
Yeah, and the asker also asks about if you can iterate on the paper reference regarding OA cartilage modeling.
That's probably Kimmo.
Yeah, okay, maybe you can answer that, Kimmo.
Sorry, is the person asking for sources on the model?
I guess we can basically say that that we will make, of course, the whole presentation available as a PDF file, and it will also be available on YouTube within a week or so. So I think everyone can get that information eventually. There are also a few other people asking. Oh, sorry. Go ahead, Kimmo.
Well, I could say something. Okay, so the cartilage model itself is based on the Wilson 2004 model. It's kind of a bit more sophisticated version of that one, and the rest of the sources you can find from the article, the scientific reports article.
Okay. Yeah, that actually sums up a few of the other questions that have come in about the material models. There's also one person that asked if you used hexahedral elements or use any specific software for the FE modeling.
Oh yeah, so we use hexahedral elements, the C3D8P model. So it's a porous cube essentially, with 8 nodes and 8 integration points. And what was the other part?
Yeah, and if you used any specific software for doing the finite element analysis.
Oh, okay. So we used Abacus, which Abacus and FE Bio are usually the most popular ones. FE Bio is a free program, by the way. It's very competent. So if you want to do this kind of research, but don't have the funds to buy Abacus, then go with FE Bio. But the way that we implement the custom material model is that it's basically calculated using a custom MATLAB script, and then it's the sort of equations have been written in a Fortran file, which is then linked into Abacus. It's kind of complicated to do that, but we manage.
Yeah, but maybe that also links to another question that's very related to this. How is the FE model included into the model musculoskeletal multi-body software, and how do you actually go about that? The fact that there is a reaction between the two, like that they are coupled. And maybe Michael can answer that, because I think it links a little bit into this force-dependent kinematic stuff.
Yeah, it does. So it's a good point that if you want to capture the full, anatomy and the full details that we have in the finite element model, we would have to include it directly into the multi-body dynamics. The issue with that is that it will be very computationally slow. So the link to actually do these ones is this force-dependent kinematics model that we did. So we assumed in that model that the bones are rigid, but the cartilage is deformable. We did a simpler, representation than we did in the finite element model, where it's like an elastic foundation model, and the ligaments are also modeled non-linearly elastic as we do in the finite element model. So it's like a simplified representation of the finite element model that we have inside the musculoskeletal model, and then we pull the loads out of that. So we don't have the full finite element model in there, but we have like a simplified version of what it captures.
Yeah, I think that explains it a bit. I think we should take maybe the last two or one question now. There is one here asking that noticed that you segmented muscles. How did you use that information?
So actually we didn't segment the muscles. So we only segmented the bones out of the full lower limb scan, and then we did the morphing. And then because we have the muscle insertions from cadaver dissection, we used the morphing to generate where the muscles should be. So in principle, it is possible to segment the muscles and bring them in the model, but that makes the whole workflow even slower. So we try to come around that. There are some papers out on how to do that as well.
I think that is good. So thank you very much, Kimmo, for joining from Finland, and thank you very much.
I could easily answer some more questions if we had time, but if we have outside on time, then that's fine.
Yeah, I think we'll have to stop now. Everyone, all of this will of course be available on YouTube if you want to hear it later. But for now, I'll just say thank you to everyone who listened in, and I hope to have you all back some other time when we do some of these webcasts. But thank you very much, and have a nice day.
Thank you.